Welcome back, and we are on to lesson 9. And what we're doing right now is working different problems that have to do with energy. And in lesson 8, we focused on problems that had to do with physical processes. And in lesson 9, we're going to focus on problems that have to do with chemical reactions. And remember that when we're dealing with energy and chemical reactions, that most of this business has to do with compositional potential energy, that the energy that is absorbed and released when bonds break and then when bonds are reformed. All right, let's get started. Question number one says, when two chemicals mix, their temperature drops. Wow. All right, their temperature drops. So what I'm going to do, since they don't tell us anything about the reaction, is I'm going to make one up. So we have chemical A plus chemical B going to C. And to solve this problem, we need to actually draw a picture. So I'm going to have a big box here. And this describes our surroundings. You guys should be familiar with this. We've been drawing images like this for a while now. And on the inside is where we're going to put our system. All right, and what we've been directed to understand is that when we react this A plus B to make C, all right, that the temperature goes down. Now, the author of this question really didn't stipulate too much, and actually I think it would be fairly easy to get confused here. So I'm going to be really explicit. When we start the experiment, all right, and what I mean by that is we have our surroundings, right, and we take A and B and we mix that into the water, all right, and A and B start to react. What's going to happen is the temperature is going to decrease. So T1 here is going to shift, and we're going to see a decrease in the temperature. So if I was to illustrate that this way, we would say that T2 is going to be less than T1. What does this mean in English? Okay, so say you're holding a glass of water, and you take compound A and compound B and toss it in there and then stir it around, right? You would feel the glass cooling down in your hand. So if you'd started out with that glass of water, say at room temperature, like around 25, it's going to cool down. And whatever the final temperature is, which we can't figure out from this example, it will be cooler than room temperature. And a human will perceive this as the glass getting cold in their hand. All right, now, how does that happen? The only way that the surroundings can cool down, right, the glass is going to get cold in your hand, is if the kinetic energy of the surroundings, of the liquid, are transferred into the kinetic energy of the system. So in here, it's going to be plus Ke. And that's what's actually driving this reaction to make C. So relative to the system is actually endothermic. All right, and relative to the surroundings are exothermic because they lost energy to the system, which drove this reaction of A plus B. All right, let's move on to question number 2. What do they say here? All right, wood burns to release heat, light, and sound. I'm going to read that again. Wood burns to release heat, light, and sound. So again, what I'm going to do is draw a picture of this. And we're going to have two boxes. One is the surroundings, and then we're going to have the one on inside here, which is going to be our system. All right, and let me just get that in here. All right, and then we're going to have wood plus oxygen. This is a combustion reaction we're talking about, right? Let me read it one more time. Wood burns to release heat, light, and sound, all right? So this is a combustion reaction. It's going to make CO2 and water and some other, along with some impurities. All right, and then it says that the wood is burning. It's producing light, so it's producing flames and whatnot. So campfires are hot, right? So I shouldn't have to. It's not rocket science that the Ke here is going down and we're gaining in the surroundings, right? When you stand next to a fire, it's warm. And that's because energy is coming from the fire into the surroundings. So for this example, the system is losing energy, so it's exothermic, all right? And the surroundings is gaining energy, so it's endo. Now, let me see if I can fit this next one in here. So I'm just going to draw a line straight down this thing. All right. Okay, when two chemicals mix, their temperature rises. Their temperature rises. All right. Again, this is worded pretty badly. Let me read it again. When two chemicals mix, their temperature rises. Okay, here's what they mean by that Russian. Again, we have A plus B going to C, because we need an illustration, right? We're mixing two chemicals, let one be A and the other one's B, and obviously in a chemical reaction we're going to make a product. Keep it simple. Again, what I'm going to do is I'm going to draw my diagram. And like we've done in all the other problems, this is going to be my surroundings. All right, and inside this we're going to have our system. Hopefully you're getting the hang of this. All right, here's my system. And then the system is the reaction, so we have A plus B going to C. And what do they say is happening here? The temperature rises. All right, so that statement is a reference to the surroundings. So the surroundings, T rises. Now think about what that means. The only way that the temperature could be going up is if we're actually gaining kinetic energy out here. So let me just write that, plus Ke. And if we're gaining kinetic energy out here, that had to come from somewhere, and the only place it could come from would be the surroundings. I mean, excuse what I said. The only place it can come from is the system. All right, that's this value right here is a system value, and it's moving into the surroundings, and that's the reason why the temperature goes up. All right, so the system in this example is losing energy, therefore it's exo, and the surroundings is gaining energy, and therefore it's endo. All right, now let's keep moving here. So I'm going to move to another screen. All right, here we go. All right, so this is going to be question number 4. Two chemicals only react if you heat them constantly. All right, so this has equally confusing language in it. So this is problem number 4, and again we're mixing two chemicals together, so I'll just call them A plus B again, and when they do react we're going to make a product C. And we're told in this that the two reactants are not reacting unless we heat them. So let's draw a picture of this again, and then we'll fix this so it's consistent with what we're being told in the problem. So here's my system. And again, this is the surroundings. All right, and our system is the chemical reaction, so it's A plus B, and then going to C. We're told in the problem that the reaction cannot proceed unless it's heated. All right, so what does that mean to you? I mean, how is this going to be heated if the only thing that we have going on is the surroundings completely surround the system? All right, well, hopefully what that means to you, let me change the color here, is that the surroundings are going to have to provide the energy to drive the reaction. And how is that going to happen? Kinetic energy is going to be delivered to the system. I'll use a darker color so that it can overlay this. So as long as we have energy entering the system, then our reaction is going to go forward. So what does this mean then? Well, for the surroundings, since the kinetic energy is leaving, this process is going to be equal to exo, right? It's going to be exothermic. The energy is moving from the surroundings into the system in order to drive the reaction. And the system, because it's gaining energy, is going to be endo. Okay, now let's go to the fifth one here. And let me read it out loud to you. It says, plants take in light energy for photosynthesis. All right, plants take in light energy. All right, how are we going to, I think we can do it this way. I'll just use P as a plant, and then I'll just spell out the word light, and then we'll use an arrow, and then we get energy in the form of ATP. Okay, so again, what I'm going to do is draw our boxes, all right? And we're going to have our surroundings, all right? And then we're going to have our system on the inside of that. All right, and here's my system. And we're going to have P plus light to generate a product. I'll just call it C, all right, to keep things simple here. And what is the information in the question? It says plants take in light energy for photosynthesis. So the energy has to come from somewhere. It's going to come from the surroundings, all right? So let me change the color again. So how do we want to represent this? You know, because I've used kinetic energy all the way through this, but I think it's a little inaccurate right here, because really the energy that they're talking about is the input of the sun, right? So here's what I'm going to do. I'm just going to call this negative E. And remember, the negative sign doesn't mean lack of energy. It tells you direction. And the direction is the energy is moving from the surroundings into the system. And it has to move into the system because it's required to drive photosynthesis, right? So the system's going to gain that energy where it's going to be used to drive this reaction. So this has to be plus E. That doesn't change anything that we've been talking about, since the surroundings are losing energy. The surroundings are going to be exo. And our system, which are these reactions, are going to be endo. It takes energy to produce energy, actually. I mean, that's sort of the take home right here. All right, and I think we have room for the last two, so we're going to go for it. I'm just going to draw a line right down the middle. So number 6. Now, you've actually seen me do this. Basically, what the author's doing is it's giving us a chemical reaction, so I'm going to write it. All right, so this is what we've been given in the problem, and we have to determine whether it's exo or endo. So remember what I said a few videos ago. When you have a reaction that is exothermic, you can treat the energy that's released as a product, and here it is. They've actually written it in here for you. All right, the heat is here as a product, so it's being produced. If I'm going to draw my boxes again. So here's my surroundings. All right, and in the middle of this, again, we're going to have, see, you have the same scenario every single time. So I'm going to draw my system in here. And then we have our chemical reaction, which is always considered our system. All right? And as this thing goes, it's producing energy. So we can write that here, plus E. Well, where's it going to go? It has to leave the system and it will enter the surroundings. Whoops, I made a mistake. Let me fix this very quickly. Okay, so the chemical reaction is indeed producing energy. All right, but the energy does not remain in the system. So we need to have a negative sign here. And it is going to enter the surroundings, because remember, for reactions that produce energy, the surroundings are going to warm up. The temperature is going to rise. Actually, let me just put that in here. Temperature rises. And the only way that can happen is that you have energy that's leaving the system and it's going into the surroundings. So this reaction is XO. The reaction is XO. All right, and then lastly, we're going to have problem number 7. Let me read it to you. When cold H2O is added to sulfuric acid, it rapidly reaches the boiling point of H2O. All right, so H2O is being added to, based on what the author wrote here, we're going to assume that the H2O was added directly to pure sulfuric acid. So again, I'm going to have my 2 boxes. Here's my surroundings. And here I'm going to have H2O plus sulfuric acid to make some kind of product. We'll just call it C. And it is producing energy, right? So again, like in the last problem, the energy is going to immediately leave the system, and it is going to enter the surroundings. And in this scenario, like in the last one, what's going to happen is the T is going to rise. So if you were holding this reaction in your hand, right, you have a glass of water, you add some sulfuric acid to it, you would feel the glass heat up. This is also true in problem number 6. All right, so basically in the surroundings, this process is endo. It's going to gain in energy, and that's why the temperature rises. And if a human's holding the glass of water, it's going to heat up. If we look at from the system's perspective, this is exothermic. As the energy is released, it's going to move directly into the surroundings, and it's going to cause the temperature of both the combined surroundings in the system to warm up. So the system is XO. All right, and with that, this concludes the video, and we'll see, actually, after I've had some interaction with you guys, what happens next. So we'll see you on the other side.